So in this video, we are going to perform modal analysis on a plate with a lump mass attached to it. So just to have a background, what is modal analysis? So modal analysis is basically used to get the mode shapes of an object under different conditions. So what are mode shapes? You might think. So mode shapes are the deformed shapes which the structure takes when exposed to external excitation, which resonate with its natural frequencies. So how do these mode shapes look? We'll exactly see when we perform the analysis. Okay. So to perform the analysis, we will need a plate, a lump mass. As you can see, we already have the plate and the lump mass here. So this is the plate, and I've already meshed it, and it's concentrated into. This is the lump mass. So just in case you are imagining how to create this lump mass, so for that you have to first create a node, which you can create by going to geometry and then nodes, and then you can select any of the options to create node. If you know the coordinates, you can directly put in the coordinates and create the node. Okay. Then after creating the node, you have to go to 1D and go to masses, and then you have to select the node from here under nodes and assign a mass to it, and it will automatically, the concentrated mass element will all automatically get created. Okay. So we already have the plate and the lump mass. So now we'll constrain the plate and connect the lump mass to the plate. So for connecting the lump mass to the plate, we'll use RB3 elements. For that, we'll go to 1D. We'll go to RB3. Then we'll select the node, and then we have to select the places where it is connected. So basically in this model, we are going to connect this lump mass to this 4 inner holes that you can see here. So we are going to connect it on the faces. So select faces from drop down here. We'll select these faces. Okay. So then we'll click. Okay. So we have to create a element before that. So we'll name this element as RB3. So we change the color of this element just in case of okay. So we have the node selected, we have the faces selected, and the current component is RB3. So we'll click on create, and it will create the RB3 elements as you can see here on the screen. So the lump mass is now connected to the faces of these holes. Okay. Now we have to constrain this plate. So then for that, we'll go to analysis and constraints. So before that, we'll go and create a load collector. For that, you can go to this white browser area, and you can go to create, and you can go to load collector. Okay. As constraints. Okay. So now to apply constraints, we go to analysis, constraints, and then we'll select the faces which we want to constrain, the nodes. So in this case, we'll constrain through this 6 hole on the outer circle. So we'll select this 6 hole by faces. Okay, so we have selected the 6 holes. Then we'll check all the degrees of freedom, and the value is 0. We'll click on create. So this we have applied constraints. Okay. So after that, now we have to assign material to this plate. Okay, so I've already created a material called steel. So we'll be using steel, this is default material available in Hypermesh. So if you click here, you can see the values of steel are already there, EG, mu and rho values. So if you want to create a material, you can just right click on this browser area again, go to create and select material. Material node collector will open, then you can input the values for steel. The values for steel are by their default, so you can just click on E and then press enter and it will automatically bring in the value for each mu and rho for steel. Okay, so we'll apply the steel material to vibration plate. So we'll go and apply material, select the material as steel. Now we have to apply the property also. We've created a property already, so I've named it solid property, and the card image for this property will be solid. So we'll assign this property to the vibration plate also. Okay, as you can see, solid. So we have assigned the property and material to the vibration plate. Okay, lump mass we don't need to assign anything. For RB3 elements also we don't need to assign anything. We have the constraints in place, we have the material and properties in place. So there's one more step involved here. So just before going performing the analysis, we have to create one more load collector. So we'll right click on load collector and select create. We'll name this eigl. So this load collector, we have to create a load collector called eigl. The card image for this load collector will be eigl. So, and as you can see, when I select the card image here, I get more fields to input some values like V1, V2, ND, message level, max set, etc. So, first of all, what is this eigl? So, eigl stands for real eigenvalue extraction by Lanczos method. So, basically, what our eigenvalues are? The solutions for the equation. So basically we are extracting the solutions to the equations, we're solving the equations and extracting the solutions. Those are eigenvalues. So the eigenvalues here represents the modes or modal frequencies of the structure. So to get a brief on the fields here is V1. So V1 is basically the starting frequency. If you suppose you have a range of frequency which you want to check if the structure has any natural frequency, so you can enter V1 and V2. V1 starting frequency, V2 is the ending frequency, that is V1 is the lower bound and V2 is the upper bound, between which you want to test if the structure has any natural frequency with which it can resonate with an external excitation. Okay, so ND is the number of this is the number of modes ND. So you can put any number of values here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So according to that you will get the number of solutions. So suppose you put a value of 6, which we are going to use now. Put 6 here. Okay. So this will give you the first 6 modes of vibration of this plate. Okay, so we have created the plate, we have applied the constraints, we have connected the lump mass, we have created a load collector called eigl, which is used to get the solution for modal analysis. Now we'll create a load step. So to create a load step, we have to right click on this browser area again, then we'll go to create and then we'll go to load step. Okay, so we'll name this as modal analysis. Okay, now we'll change the analysis type from generic to normal modes. Okay, then SPC. Now we have to give the constraints here, SPC. So just to recap, SPC stands for single point constraint, used to define the constraints, not define, it's used to select the constraints which we have applied to the structure. Okay, so we have selected the constraints. Now this is the method. So under the method, we have to select the eigl, a load collector. So that means that the solver will use this method to extract the solution from the equation, and the number of solutions will be the number of modes that is defined inside this eigl load collector. Okay, so we have selected SPC, we have selected method. Okay, so now we are good to go. So we'll start the analysis. So to perform the analysis, we have to go to analysis, Optistruct. Okay, export options will keep as custom, run options analysis, no option will be default. Okay, then we'll click on Optistruct. So once you click Optistruct, pop-up window like this will open. So this basically shows the progress of the analysis. So here you have the message log, you have the optimization summary, and you have the progress. So this will run for some time, and when it's over, it will show as completed. As you can see here, showing message for the job, analysis completed. Okay, so uh, now we have the option to view the results. Now this is to visualize the result, and apart from that, we have an option called view here, and beside that there's a drop down menu from where we can select the output file. Okay, so we'll first see the output file. So we'll go to the drop down menu and click on the output file. So as you can see here, we have opened the output file. So this is how it looks like. So we basically have here the FEM model data. So we have the number of grids, number of elements, number of rigid elements, etc. Okay, and the type of elements which are there, serpent, concentrated mass, etc. Okay, so we'll go down. So this is the area which we are interested in. So here, as you can see, it's written analysis results, and down here we have a table. Okay, so here as you can see, in that mode there are 1, 2, 3, 4, 5, 6 modes which we had requested for, and equal to 6. So after this, you can see here there's a column for frequency, eigenvalue, generalized stiffness, generalized mass. Okay, so these frequencies are basically the natural frequencies at which the structure will vibrate. Okay, and if any external excitation similar to this frequency is supplied, then the structure might resonate, and it might there might be some deformations or some abnormal behavior in the structure. Okay, so this is the frequency. Then we have the eigenvalue, generalized stiffness, and generalized mass. So basically, if you want to know how these are related, so basically these are related by equation omega equal to under k by m. So what is omega? Omega is this frequency. Okay, and k is the stiffness, and m is the generalized mass. Here it's taken as a generalized mass, but generally when we solve for the frequencies, it's the mass of the structure. Okay, so as you can see, if you notice here, this eigenvalue and this generalized stiffness value are both same. So basically, we are getting different frequencies for different stiffness values for this structure. Okay. So now we'll be visualizing different modes for this structure. Okay, so to visualize the different modes for the structure, you can go here on the left side, and as you can see, there's mode 1. Then if you click on this down next button, you'll get mode 2, mode 3, mode 4, mode 5. Okay, so we'll start with mode 1. So we'll visualize how it's moving, or how it's vibrating. So we'll go to information, okay, and then we'll play the simulation. So as you can see, there's some movement here. If you can notice this, speed it up. As you can see, it's vibrating like here. Okay, so this is for mode 1. So we can go to mode 2. So as you can see, for mode 2 it's vibrating like this. Okay, we'll go to mode 3. As you can see, for mode 3 it's vibrating like this. Okay, so basically you can visualize different modes, and the number of modes you want to visualize you can input in the eigl card, eigl card, and then you can visualize it here, how the structure will behave. Okay, so this is how you perform a modal analysis. So this is the simplest example of a modal analysis which you can get. Okay, but the steps remain almost the same. There might be a few modifications, but this is the basic process how you perform a modal analysis. Okay, so this is all for this video. Thank you for watching this video. Just in case if you want to know more about Hypermesh, more about analysis, FEA, FEM, you can go check out my blog. It's given in the description, and I'll pin it in the comments also. So please like, share, and subscribe. See you all in the next video. Thank you.